All right, chapter 6. So we're going to leave that. There's some questions hanging, about atoms and their properties. And so we're going to leave that question hanging there, and we're going to come back to it later. And so that was just kind of getting the basic understanding of some of the structure and composition of atoms, but we need more, to really be able to correlate things with properties, and we need a better understanding of properties. The chapter 5 PowerPoint, can you send chapter 5 PowerPoint? I believe you only sent chapter 6. Okay, I guess I forgot. Did I forget to post chapter 5 PowerPoint on Piazza? I'll take a look. But yeah, I'll make sure to do that. All right, chapter 6 PowerPoint here, nomenclature. Let's take a look at that. And so this is the element sodium here. If we look at sodium, sodium has this, what we call metallic lattice structure. And if we look at the simplest unit of sodium, it's just a single atom. So we can break this down into a single atom, and that would be a sodium, the smallest piece of sodium. And so the formula, we call it an empirical unit, but the formula would just be Na, and it's a solid. So we call this Na solid. Natrium is sodium. And so chlorine, though, the smallest unit of chlorine, of this gas is Cl2, which is a molecule. And so we have a lattice here. This is a small. If we can break these molecules up, if we break them up, it becomes less stable chlorine atoms. Like this, and these are very, very much more reactive. This green gas here is quite reactive as it is, but atomic chlorine, this is called atomic chlorine. This would be molecular chlorine. Molecular chlorine is the preferred state for chlorine. It's a bit more stable than atomic chlorine, but still chlorine is very reactive. Sodium is very reactive. In fact, if you take sodium and mix it with chlorine gas, you get a very violent reaction. This is a violent reaction between sodium metal and chlorine gas. You knock the stopper. This is a rubber stopper. Knock that stopper off. This is sodium chloride. Sodium chloride is, clear, colorless. If you look at a single crystal, there's no color there. This is lattice structure. This is a metallic lattice here. This is salt lattice. The smallest unit of this metallic lattice is just a single atom, sodium, like that. The smallest unit of this salt lattice here would be 1 sodium and 1 chloride. That would be not a molecule like this. This is a molecule. It's not a single atom like this. It's what we call a formula unit. And so the formula unit would be NaCl, solid here. And so this chemical reaction is a reaction between sodium metal and chlorine gas to form sodium chloride, salt. Now, when we look at this reaction, I have 1 sodium, it ends up here. I have 2 chlorines, I'm missing 1 chlorine. And atoms are neither created nor destroyed. And so the easy fix to this is to just bump this up to 2 sodiums. If I have 2 sodiums and 2 chlorines, then I'll get 2 sodium chlorides like that. And this is called balancing the equation, balancing the equations to make sure that all atoms are accounted for in this. Let's see what this reaction looks like. This is a little video of the reaction here.
The reaction of sodium metal with chlorine gas is quite vigorous. Another way of saying this is that the formation of the ionic compound sodium chloride is very energetic, releasing considerable heat and light.
So that was a pretty vigorous, violent reaction there. I mean, you saw the big flame. And essentially, this is like, it's not burning, in a way it's burning the sodium to form this product here. In another way, well, I guess it is burning. In another way, it's not. because usually when we burn things, we usually think of oxygen, but this is a different thing. Chlorine's similar to oxygen in the sense that it's an oxidizer. Oxygen's the prototypical oxidizer. Chlorine's an excellent oxidizer. Sodium is what we call a good reducer of fuel. And so this is a pretty violent reaction. This produces a lot of energy. Now the energy, oftentimes we leave off the energy, you know. This would be highly endothermic or highly exothermic, this particular reaction. What would we say, endothermic or exothermic? Exothermic, good. And so oftentimes, this is not required to do, but to balance this in terms of energy, we need to make sure that we account for the energy here. Energy is a product here, it's exothermic, and so it's a product. But oftentimes we don't balance it in terms of energy. We just balance it in terms of atoms here. Okay. In terms of energetics, sodium metal and chlorine is less stable or more stable than salt, sodium chloride. Which one is more stable? This or this? The reactants or the products? Yeah, the products are more stable. And so in terms of our energy level diagram, it would look like this, where we plot the total energy or the internal energy U over up here, and we put two sodium solids up here, plus the chlorine gas here. This is highly exothermic, and it's going to produce two sodium chlorides, which are going to be lower in energy. Now, the first law of thermodynamics says that energy is conserved, and so we're going to lose energy here. The energy that's lost, delta U, is going to, well, let's see here. What's different is, let's wait until, we'll start out at 25 degrees C here, and we end this at 25 degrees C. So a lot of heat's generated, but we'll wait until the heat dissipates and it cools back down to room temperature. And so that's going to release the maximum amount of energy. So the kinetic energy doesn't change. So delta KE is 0. But the potential energy does change, and this has a very high potential energy, sodium and chlorine gas. This is a very low potential energy, so that potential energy. Now that potential energy is going to be evolved in the form of heat and work. The heat, you can feel the heat. The work, you heard the sound. This would be work, popping the stopper off. The flask, this is called a round bottom flask, by the way. This is volumetric flask here. Or no, maybe that's a round, no, that's a volumetric. I don't know why they put it in volumetric flask. A work could be light generation, you know, or shooting little particles out, that kind of stuff can happen in heat and work here. And so that's what we got. Well, anyway, we're talking about nomenclature. And so this is an element here. And the name of this element is sodium. And so we could call this sodium metal or solid sodium. And this would be chlorine. This is also an element, but this is a diatomic element. You know, the formula for chlorine typically is taken as Cl2. This is what we call a compound. A compound is two or more elements that are chemically combined, that are bonded together. And this compound is called sodium chloride. And so we're going to be looking at naming things. If you want to be more specific, this would be called diatomic chlorine or molecular chlorine versus atomic chlorine. This is molecular chlorine. If it's not indicated, then we assume it's molecular chlorine because it's more stable. This is helium here, a helium tank, filling a helium balloon. So this is helium. Helium occurs as just atoms, helium atoms. So this is helium gas. And so the formula, nomenclature is naming and writing formulas. And so this is helium gas. Yeah. Over here, this is hydrogen. Hydrogen doesn't like to be alone. Like helium's fine being alone, so helium is just atoms. Hydrogen likes to pair up. And so hydrogen, like chlorine, likes to pair up in diatomic molecules. So this is molecular hydrogen. Atomic hydrogen is also available, but it's less stable. Atomic hydrogen is more reactive. It doesn't like to be alone. Helium doesn't like to pair up. This is sodium metal. This is badly corroded sodium metal here. Do you see the black coating on there? And it's lost its metallic luster, and there's some white powder. So this is sodium metal. And the smallest unit of that would be the atom. So sodium solid here. Metallic lattice. It's badly corroded, so this is not very pure. Sodium metal there. Okay, starting off with patterns. One of the patterns that we notice in the periodic table is on the left of the metals, except for hydrogen. Hydrogen, all these are solid metals except for mercury and hydrogen. Interestingly, hydrogen at high pressures behaves like a metal, but hydrogen under normal pressures doesn't. Then we have non-metals over here. Metals all share certain traits, certain properties. Like all metals have pretty decent electrical conductivity, etc. And so metals share very similar properties. Non-metals, however, don't. Diamond is a non-metal versus graphite. Those two are quite different in terms of properties. So non-metals, we see a lot more variation in the properties. But there are certain properties that all non-metals share, and there are certain properties that all metals share, but much more so in terms of metals. And then we have metalloids. Metalloids are intermediate. They're at the border between metals and non-metals. So they have properties of both metals and non-metals. One of the properties of non-metals, except for the noble gases, in chemical reactions, they like to take electrons. They're oxidizers. Oxidizers like to take electrons. And metals are reducers. Reducers like to lose electrons. But we'll look at that later. That's one characteristic that we could say for those right now. When we look at some of these non-metals, some of the non-metals like to form diatomic molecules. And which ones are those? Well, hydrogen, which is borderline. Nitrogen, a borderline metal, non-metal. Nitrogen, although you'd think it's non-metal. Oxygen, fluorine, chlorine, bromine. There's 7 of these. These are called the 7 diatomics. And we know that they're more stable paired up than they are alone. And so we just memorize those. And so fluorine gas is F2. Chlorine gas is Cl2. Nitrogen gas is N2. So we got to remember these. These are some other molecules. These molecules, let's just figure out what the formulas are for these molecules using the rules for color coding. So for example, black is carbon, and a lot of these molecules with carbon, we write the carbon first. And so there are 2 carbons here, C2. And how many hydrogens? 1, 2. The whites are hydrogens, 3, 4, 5, 6 hydrogens, H6. And the red is oxygen. Now, C2H60, this is also C2H60. C2H60. But if you look at the structure, do you see the structure is different? Even though both of these consist of the same atoms. These are called not isotopes, these are called isomers. Isomers has the same composition but different structure for molecules. And so these are 2 isomers. This isomer is called ethanol. This one. This isomer is called dimethyl ether. Just different arrangements, structural arrangements. This one is written slightly different. This one's going to be written H2 or CH2O. Carbon, 2 hydrogens, 1 oxygen, CH2O. This one's formaldehyde. This one has 3 carbons. So C3 and then 6 hydrogens, H6, and then 1 oxygen, C3H6O. In this particular composition and this particular structure, this one is called acetone here. And so we have ethanol. Ethanol is very, very common, so you should know this one here. And ethanol is often written like this. You look at this group over here. This is a CH3, a carbon with 3 hydrogens. And this carbon has 2 hydrogens. This is a CH2. And then we have this OH attached to it like that. So it's CH3, CH2, OH. This is the same composition. But this one shows, this is called a structural formula. The structural formula is different. This molecular formula, this is called the molecular formula here. The molecular formula is the same for these two. The molecular formula is the same, however, the structural formula will be different. Ethanol has a structural formula CH3CH2OH. Dimethyl ether has a structural formula CH3OCH3. Compositions are totally the same, but the structural formula, the structures are different. And therefore, they give you different properties. People drink ethanol, you know, and it's found. Don't drink methanol. And make sure if you're using hand sanitizer, make sure your hand sanitizer is made with ethanol, not methanol. Methanol is toxic, and so be careful. And don't drink methanol. You can drink ethanol, but don't drink methanol. Methanol can kill you, or it can actually make you blind. That's not some urban legend, it's true, because methanol gets metabolized in your body to make methanoic acid or formic acid, which attacks your optic nerves. That could be, that could cause permanent damage. Okay. Formaldehyde acetone. Acetone is pretty common too. Dimethyl ether, not so common. So this would be the formula for that. The names are tricky because, you know, if we're given the molecular formula, we don't know which isomer we're talking about. And so we really need more. And these, a lot of these are just kind of memorization, but we'll try to minimize the memorization. These you don't have to know the names for, except maybe ethanol. You don't have to know the names for these, the formulas. Now, these are tricky to name, but if we have something with only 3 different elements, these have 3 elements, carbon, hydrogen, and oxygen. All these are carbon, hydrogen, oxygen containing compounds. But if we only had 2 elements, then that's what we call binary. Binary refers to 2 elements. And if we only have 2 elements, then the naming is a lot easier. You know, binary, 2 elements. We can name these a lot easier. Two element. Then it's easy. So, for example, this is not binary. This is ternary. Or is that ternary or trinary? I don't remember. However, something like this, C2H6, this is binary. And so we can name this easily. Carbon monoxide, CO, is binary. However, CH2O is not binary. This is not binary. And so rule number 1, we have to restrict ourselves to binary. We can't name these using these rules because these rules do not apply. The name of binary molecular compound is 2 words. The first word is the name of the element appearing first in the chemical formula, including a prefix to indicate the number of atoms of that element in the molecule. These are the prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. The second word is the name of the element appearing second in the chemical formula, changed to an "ide" ending. Okay. Even though this is binary, we're not going to name compounds like that. With carbon, hydrogen, there's a different naming system for those, but we can name simple ones like this. You know. And so let's look at some of these. Name. This is monocarbon monoxide, but we don't call it mono, we just call it carbon monoxide. Now, we change the oxygen to oxide, so, and we say mono, so it's got 1, so monoxide, we don't want that. And so the ending of oxygen was changed to ide. CO2 is carbon dioxide, you know. N2O4, this would be dinitrogen. Now oxygen gets changed to oxide. Tetra. Now this is tricky, tetraoxide or tetroxide? We drop a double vowel. So rather than calling it tetraoxide, we call it tetroxide. Let's put a single vowel in there. Dinitrogen tetroxide. What would the formula for this be? Tetra phosphorus decoxide. Decoxide. Tetraphosphorus decoxide. Well, tetra is 4, so it'd be P4. Oxide is O, and deca is 10, so P4O10. That would be tetraphosphorus decoxide. Good, P4O10. You got it. We'll do more examples of these later. Okay, these are what we call molecular compounds. Molecular compounds consist of non-metals. Did I put the periodic table in here? Yeah. Molecular compounds are compounds of non-metals, like nitrogen and oxygen are non-metals, carbon and oxygen are non-metals. When we have compounds that consist of metals plus non-metals, those are ionic compounds. And we have a different rule system for ionic compounds. It turns out one of the properties, let me tell you the chemical properties of metals. One of the chemical properties are metals tend to lose electrons when they undergo chemical reactions. And so tend to lose electrons when they react. Well, if they lose electrons, what happens is it forms what are called ions. Ions are charged particles because they have a mismatch of protons and electrons. And so let's take a look at some of these here and see if we could see a pattern in the metals here. So, excuse me, this is just what's observed. Now, looking at these here, do you see a pattern? Yeah, I see a pattern. Look at the alkali metals. The first are group 1. This is called group 1. If you look at group 1, they all lose how many electrons? Well, they all lose 1 electron because if they lose 1 negative charge, then they're going to have an imbalance. One of the positive charges are going to be imbalanced, and we're going to have a net positive charge. So these lose 1 electron. The alkaline earths lose how many electrons? 2, right? If we extend this pattern out, this pattern wasn't extended out. but I'm going to extend it out. Here comes scandium here. Scandium, guess what charge scandium is? 3+ is correct. Scandium is 3+. Guess what charge titanium is? Yeah, titanium is 4+. But to lose 4 electrons isn't so easy. So titanium is what we call a variable charge. Scandium is fixed charged. Fixed charge. It's always 3+. Scandium. Yttrium's below this. Yttrium's always 3+. Titanium, however, is variable charge because sometimes it's tough to lose 4. And so sometimes we only lose 1 and we end up with titanium plus. Or sometimes we lose 2 electrons, we'll end up with 2+. Or 3 electrons, we'll end up with 3+. Or 4 electrons, we'll end up with 4+. But not 5 electrons. Titanium does not want to lose 5 electrons. So we do not see a titanium 5+. It's very interesting. So when we have these species here, so this should be 4+, this should be 5+, this should be 6+, right? This should be 5+, this should be 6+. But when we look at it, chromium, these are the most common. So 2+ and 3+ are the most common. This should be 7+, this should be 8+, etc. Yeah. Manganese here, 2 and 3 is most common. 2 and 3 here, 2 and 3 here, 2 and 3 here. The most common charges here. So there's a little pattern. Do you see the pattern? 2, 3 is common. Then here it's kind of interesting. It's another 1, 2 pattern. Do you see a 1, 2 pattern? This is 1, although this buxotran, and this is 2. So we go here. We go 1, 2, and then 3, 4. And then vanadium should be 5, right? Vanadium should be 5+, but vanadium is variable as well. And so vanadium has plus, vanadium 2+, vanadium 3+, vanadium 4+, vanadium 5+. However, vanadium 6+, no. Vanadium 6+ is no. Chromium, it's hard to get 6+, you know, so 2 and 3 are most common. For vanadium, 2 and 3 are pretty common as well. 2 and 3. And then take a look. After we get here, it goes 1, 2, 11, and 12. And then it goes 3 here. 3, and then this is 2, 4. And so it goes, if you go look, so sodium plus, magnesium 2+, aluminum 3+. Okay. And there, then here, a tin is 2, 4. And so I'm starting to see some patterns here. Some of the patterns are this. Here. This region of the periodic table is what we call variable charge. Variable charge. And when we look at the variable charge, we're going to subdivide it. Now, this is just a rule. This is not a law. And so, you know, so it looks like the ones here are 2, 3 are very good. So +2 and +3 are very common charges. And then here is +1, +2. +1 and +2, perhaps, around here. And then around here, it looks like +2 and +4. +2 and +4. There's a little pattern I see here, as well as this pattern here. Look at this over here. You know, these like to be 0. But look at this. The halogens are all -1. -1 means they didn't lose an electron. -1 means they got an extra electron. Oxygen, -2. Sulfur, -2. Nitrogen, -3. Phosphorus, -3. And so these gained electrons. These are all called ions. Ions either lose electrons. Metals tend to lose electrons to form positive ions. Non-metals tend to gain electrons to form negative ions here. Now let's see if we can nail down this pattern a little bit more based on the charges and stuff here. Let's see. Okay, let me go to periodic table. Let's go to a decent periodic table. I'm going to go to a periodic table. Let's try to find a good one. Maybe this one. Remember I told you there are two styles of periodic tables. This is the other style of periodic table. This periodic table is different than your book because of what they do. 56, 57 drops here, lanthanum's down here, lutetium's up here. In your book, it goes 56, 57, they put lanthanum here, and they throw lutetium down here, but whatever. We'll learn how to use both of these periodic tables. Okay, one thing though is these guys like to lose one electron. So lithium, how many electrons does lithium have? Three. If lithium loses one electron, then how many electrons does it have? Well, 3 minus 1 gives us 2. What has 2 electrons? Helium. Sodium has 11 electrons. If it loses 1, then how many does it have? Yeah, it has 10. Well, neon has 10 electrons. Potassium has 19 electrons. If it loses 1, it has 18 like argon. Rubidium, 37. If it loses 1, it's 36. Cesium is 55. If it loses 1, it's 54. And so what happens is it's losing an electron, so it ends up with the same number of electrons as the noble gas. This is stable here. Beryllium has 4, and it goes plus 2. So if it loses 2, it's at helium. And so beryllium wants to do the same thing. Magnesium, calcium, strontium, barium, all these want to go plus 2, so they end up with the same numbers over here. Scandium has 21, so it wants to go to 18, lose 3. Titanium is 22, wants to lose 4 to go to 18. Vanadium is 23, wants to lose 5 to go to 18. These have to lose too many. And so it's got to lose 6. It's hard to lose 6, 7, 8. It's getting more and more difficult. Pretty soon you reach this point, like, okay, we go beryllium has 4, then we go to boron. Boron wants to lose 3 to be like helium. But carbon can either lose 4. If it loses 4, it'll be like helium, or it gains 4. If carbon can gain 4, it has 6 electrons. So if it gained 1, 2, 3, 4, it'd be like neon. So carbon's stuck right in the center. It could either lose 4 to be like helium or gain 4 to be like neon. Whereas nitrogen, how many would nitrogen have to lose? Nitrogen would have to lose 5. That's correct. That's good. Or it can gain 3. And so nitrogen, carbon, these are very interesting. And so let's talk about these just for a moment. And the charge is what we call the oxidation state. Oxidation state. Charge on atom. We'll have to talk more about this later. But carbon, carbon varies from carbon 4 plus to carbon 4 minus. Nitrogen varies from nitrogen 5 plus to nitrogen 3 minus. So if it goes 5 plus, then it ends up with 2. If it goes 3 minus, it ends up with 10. And so nitrogen can go either way, but it's probably easier to gain 3 than to lose 5. Oxygen's the same kind of thing. It can gain 2 or lose 6 to do that. And so the charges are going to be a result of, you know, the noble gases. The noble gases, there's something special about the number of electrons here. You know, there's something special, which we're going to talk about later when we start thinking about or hypothesizing why. Electrons here. And so, you know, we want to try to make it there. Some of these are too far, like chromium is a little bit far, you know, well, I guess, you know, manganese, it could potentially make it there, but with a little bit of help. We'll talk about that help in a little bit. So going back to this, let's go back to PowerPoint. Going back to this here, this is easy, +1, this is +2, +3, +4. But, you know, there's a gap here. So either we're in the transition block or we jump over here, like aluminum's +3. You know, this should be +4, which would be silicon here. These can go either way, you know, it's -3 seems easier, but it could also go +5, the opposite way. Here, this is -3, could also go +5. This is -2, could go +6, you know. This is -1, or it could go +7. Well, -1's a lot easier, seemingly, than +7. And then we hit the target. This is very important, the noble gases here. All right, now how do we name these? Now, what's the difference? Okay, the naming can get kind of tricky. And so this is hydrogen, but we have to call it something special. And so what we call it is the hydrogen ion. Well, we know hydrogen ion's +1 because of its location. This is the lithium ion, sodium ion, potassium ion, calcium ion. The calcium ion is always +2 because of its location in the periodic table. Barium. But now we have a problem here. We can't call both of these chromium ion because one is 2, the other's 3. So we have to have a different name for both of those. So one of them we call chromium Roman numeral 2 with no space. This is the chromium 2 ion. The other one we call chromium Roman numeral 3. There used to be an old convention. The old convention we'd call the 2 plus chromus. And in the old convention we call the 3 plus chromic. Ic refers to higher charge regardless of it, what the charge is, just the higher charge. And so here the lower charge is copper 1 in this case, copper 1. Copper 1 we call cuprous. Cuprous. Copper 2 we call cupric because it's higher charge. And so this is cupric. Cuprous goes to the lower charge. Aus goes to the lower charge, it goes to the higher charge, regardless of what that charge is. And so we look at tin here. Tin, we use the Latin name, stannous. Stannous is the lower charge. Stannic is the higher charge. In other words, stannous is tin Roman numeral 2, and stannic is tin Roman numeral 4. That's how we name it. And so those are cations. So with fixed charge, we never put Roman numerals. So we'd never say sodium 1 here. We'd never do sodium Roman numeral 1. That's wrong. We just say sodium ion. And we know the charge on sodium ion. The same thing here. We only use the Roman numerals when we're doing variable charge. And variable charge, where does variable charge occur? Variable charge occurs in this region of the periodic table. This is fixed. except for 3 elements. You know, this is an ocean of variable charge, but there's a little island of fixed charged elements in the variable charge region. Let me go do something really quick. Okay, so in the variable charged ocean here, there's a little island of fixed charged ions that do not require Roman numerals. And this little island we have to have memorized. And that is zinc, cadmium, and silver. These 3 are fixed charged. And so, for example, silver, we would name silver ion. We'd never say silver Roman numeral 1. Cadmium would always be, cadmium ions always +2, and zinc ions always +2. And so there's a little island here of fixed charge, +2, this 12, or 2b. This is 1b, 11. And so this 1-2 pattern repeats. This is 1-2 pattern with A. This is 1-2 pattern with B. And so 1 is mostly +1 here, although copper bucks that. And 2 is these, although mercury bucks that. Okay. All right, so this is a little fixed charge here, island, in a variable charge C. These are called cations over here. These are monatomic. Monatomic means 1 atom ions, monatomic cations. Then we have monatomic anions here. Anions are negatively charged, cations are positively charged. So this is cations, positive. And then we have anions, which are negative here. Now the anions, we have to change the ending. For monatomic, we change the ending to "ide." And so this is called fluoride. Fluorine gets changed to fluoride. Chlorine gets changed to chloride. And so we know it's an anion because of the "ide" ending here. This is oxide. This is nitride. This is phosphide, sulfide, bromide, iodide. So we just change the ending there. Yeah, the goal for the charge, right? It's not, it's a little bit more tricky than that, but that's one way of thinking about it. Yeah, that's right. For right now, think about it that way, and then we're going to look at it in more depth later. That's how you can figure out the charge, monatomics. Okay, so know this, know the fixed charge, variable charge, island of fixed charge. Know those. Know how to get the charges. +2, +3 in the variable charge is over here on the left. 1, 2 is in the middle, and 2, 4 is on the right. That's a pattern. Now we have a little bit more complicated ions. We have something called polyatomic ions. Polyatomic ions are made up of more than 1 atom. We have polyatomic cations and we have polyatomic anions. There aren't very many polyatomic cations, so the easiest thing to do is just to memorize them. And so what are the polyatomic cations that you need to memorize? And so let's look at these guys here first. And so the polyatomic cations are going to be a couple of common ones. NH4 plus. NH4 plus is called ammonium, or ammonium ion, you know, ammonium. What else is polyatomic? Oh yeah, there's one more. This is a weird one. It's Hg2 2+. This is diatomic mercury, but it's a diatomic mercury ion, Each mercury is +1, and we have 2 of them, so it's +2. And so this is called mercury. Mercury is variable charge, so there's mercury 1 and mercury 2. Mercury 1 is polyatomic, mercury 2 is monatomic. And so mercury 2 is just Hg with a 2+ charge. That's mercury. That's the polyatomic cations. What about polyatomic anions? Well, the polyatomic anions, we have 3 types. The ones that end in IDE, the ones that end in ATE, and the ones that end in ITE. So this is an ATE here, so that's like that. And this is an ITE here, so it's like that. And so let's look at the ones. This is polyatomic ides. And so 2, let's say polyatomic ides. When we see ides, we typically think monatomic, chloride, fluoride, bromide, oxide, nitride. We normally think monatomic. And so ide typically means monatomic. Typically means monatomic. 1 atom, like Cl-, that's chloride. However, there are some polyatomic ides that you just have to memorize. What are the polyatomic ides that need to be memorized? Well, the polyatomic ides that need to be memorized are things like OH-. OH- is called hydroxide. O2, 2-. O2, 2- is called peroxide. I'm going to add one, not in your book. I'm going to add O2-. O2- is called superoxide. Superoxide is important in COVID-19, coronavirus. And so I'll talk about superoxide. What else do we have? We have Cn-. Do you know, does anybody know what Cn- is? Cn- is cyanide. What else with the ides? I think that most of the rest are monatomic, so we're okay. 2, let's look at the polyatomic 8s. If we look at the polyatomic 8s, then there are 2 ones. We look at the ones based on the periodic table. Yeah, HCl would be called hydrogen chloride. That's right. If we named it as binary molecular, it should be hydrogen monochloride, but we name it as ionic, so hydrogen chloride. Oh, that reminds me of one I forgot over here. One polyatomic cation I did forget is this H3O+. H3O+ is called hydronium. Hydronium ion. So the polyatomic 8s, we start off like this. The periodic table is carbon, nitrogen, oxygen, fluorine, chlorine, bromine, here, iodine. So the polyatomic 8s, these are what we call oxyanions. And let me know what the pattern you see here is. You come up with a pattern. These are just what's observed. So the first one's carbonate element, carbonate. And carbonate is CO3 2-. Actually, you know what? I want to go one more. Let me go one more. Boron. The first one is going to be borate. Borate is BO3 3-. That's borate. And after borate, we have carbonate. After carbonate, we have nitrate. Nitrate is NO3-. Then we're going to skip oxygen and go to fluorate. Fluorate, there's no oxate here. So fluorate is FO3-. And then we go to chlorate. Chlorate is ClO3-. And then we go to bromate. Bromate is BrO3-. Don't get it confused with borate. Borate is BO3 3-. Bromate is BrO3 1-. Then we go to iodate. Iodate is IO3-. Do you see a pattern? You recognize a pattern there. Three oxygens. All of them have 3 oxygens. All of them. Do you see a pattern in the charge? I see a pattern in the charge. Yeah, the pattern in the charge goes 3, 2, 1, and then stays at 1. Do you see that? 3, 2, 1. And I see one more pattern for boron. Do you know what group boron is? What group number boron is? Boron is in group 13 or 3, or Roman numeral 3. A. This is 3A. This is Roman numeral 3A. And so boron is in group 3. Well, borate is 3,3. Do you see it? 3, 3, 3. So I don't memorize these. I see a pattern. And in order to figure out all the formulas here, I only memorize borate. If you have borate memorized and you know the pattern, then you only have to memorize one to figure out all the others. And so what I do is I don't do like flashcards or anything like that. I try to look for this kind of thing. Here you have to do flashcards or whatever, rewrite it. The way I memorize these is I just write it. And once you write it down like 50, 100 times, then it goes into your motor memory. But this is the periodic table pattern here that we see. And so no borate. If you know borate, then you know all these 8s. Okay, but there's more 8s. And so what are the other 8s that we're dealing with? And so this is what we call the outer block, or what I call the outer block here of 8s. Let's see. Like that. Then we have inner block of 8s. The inner block is going to start at silicon and silicate. Silicate is important in geology. Silicate is SiO4, 4-. This one is easy to remember because this is group 14 or group 4A or Roman numeral 4A. So it's 4, 4, 4. It's group 4. It's got 4 oxygens and it's got a 4- charge. So I memorize this one. This is the inner block. So next to silicon comes phosphorus. Phosphorus is here. And next to phosphorus comes sulfur. It's here. So phosphate. Phosphate is PO4 3-. Here, that's phosphate. Sulfate is SO4 2-. Let me do some more. Below phosphorus is arsenic. And so arsenate Arsenate is ASO4 3-. And below sulfur is selenium. And so selenate is SeO4 2-. This is selenate. Below selenium is tellurium. And we have tellurate. Tellurate is TeO4 2-. Tellurate. So do you see a pattern in the inner block? There's an inner block pattern and an outer block pattern. And the inner block pattern, shown here. Inner block pattern actually extends. I mean, inner block pattern, like germanium, comes below silicon. Yeah, 4 oxygens. And so we could do this. Let me do this really quick. So below silicon is germanium, Ge, and we have germanate, GeO4, 4-. Germanate. Actually, I don't want to box that. We just need to memorize one. We can figure out the pattern from there. Okay. All right, so there's very little memorization. Like I said, we want to minimize memorization by maximizing patterns and trends and that kind of stuff, laws. You don't have to memorize a whole bunch of observations. Unfortunately, not all the 8s fall in here. So we have the periodic table 8s, and then we have the ones you have to just memorize. And those will right over here. These are the rote memorization 8s. And so what are those? The ones that require just straight memorization are well, we'll just start off with permanganate, MnO4-. This is permanganate. Permanganate. Then we have chromate, CrO4 2-. This is chromate. Then we have dichromate, which is CR2O7 2-. This is dichromate. You'd expect it to be CR2O8, but we lose one of the oxygens to form the link that links up the 2 chromates together. So we got permanganate, chromate, dichromate, and then we have things like, what else do we have? Acetate, just go with that. Acetate is C2H3O2-. This is acetate. Or another way of writing this is CH3COO-. This is another way of writing acetate. This is what we call the structural formula, condensed structural formula. This is just the regular formula. So this tells us more information. So we got permanganate, chromate, dichromate, acetate. Oxalate is another one that's quite important. C2O4 2-. That's oxalate. Oxalate. There's more, but some of these other ones aren't as common, perhaps like cyanate, CNO-, etc. Am I missing any others that are important? Maybe. Let me take a look at something here. And what I'm going to take a look at is our supplement. Let's see what our supplement tells us to memorize. Oh, I gotta get rid of all those drawings. Let me save these drawings. So let me see, 1, 2, 3, 4, 5. I got 5 of those. Let me delete these drawings and go here. So these are important elements, but I have more. You know, I want you to fill out this more. This is not enough, I think, you know. So I want calcium, and then what did I have here? Scandium, calcium, scandium, titanium, vanadium, and then zinc, and then gallium, germanium, arsenic, selenium. So I want you to know the first 1, 2, 3, 4 rows, Harley, and then some others, you know, in here, you know. We need to know, what was the little L shape there? Zinc, cadmium, silver, that's a little island. Tin, lead, that's pretty important. Xenon was pretty important. So I already wrote those on there. Here's the monatomics, +1, +2. This is +3 right here, always +3. These are fixed. I'm gonna write that in here. This is from the supplement, by the way. These are always +3, and then it goes variable. These are variable. This is fixed. So it's +3 here, it's +3 here, it's fixed and variable. And then we have this little island of fixed. This is a little island of fixed. All the rest are variable. +3, then minus, -1, -2, -3. Or it could lose too, you know. Carbon's -4. Carbide is C4-. Let's move on. When it's okay, when it's fixed charge, we don't need the Roman numeral. So all these are fixed charge. When it's variable charge, we need the Roman numeral. So these are all variable charge ones here. Okay, I guess it's time for, let's take a short break right now. This handout you're supposed to buy, this is required material for the class. It's actually quite big, so this is what they call the, did you guys, for the class, you have to purchase the lab manual supplement plus the textbook. And so the lab manual supplement is not that expensive. It's only like 10 bucks or something. It's cheaper than going and photocopying it or printing it out. So if you took this and you printed it out, it probably cost more than just buying it at the bookstore. It's only 10 bucks. It's not online. It's at the bookstore. Unfortunately, you have to buy it. I can't distribute it because it's for the department. But yeah, order from the bookstore and just pick it up so you have a copy, and then you can write in it, you know, and fill it in. There's a whole bunch of things you got to write inside of it and turn it in. And so rather than, I'm telling you, rather than printing it out, it's cheaper just to buy it. Okay. Here's our mercury 1. Mercury 1 is a polyatomic ion. This is mercury 1 ion or mercurous. These are the ions here. Some monatomic anions here. There's a polyatomics. Let's see, we're looking at the 8s, right? And so we had acetate, chromate, dichromate. What are the 8s? Oxalate, we did that. Permanganate, we did that. Carbonate's on the chart. All these other 8s are on the chart. And so that was it. What do you mean by can't access the bookstore, Stephanie? The bookstore has a, oh, you're not in the country anymore. That is a problem. Well, ask somebody in class, you know. Yeah, this is not published by Cengage. This is published by El Camino. And when we get to the labs, you're going to need it when we get to the labs, primarily. I'm just looking at this because this just has some exercises. All this stuff we're going to cover anyway, so don't worry about it. If you don't have this, you don't need it. But you do need the lab stuff. And the labs you're going to have to, but the labs we'll see when we get there. Okay. All right, let's take a shorter break. I mean, we're just going to 6:05, so let's take like a 5-minute break right now, and then we'll start up again. Or 10-minute. What do you want? 5-minute or 10-minute break? Or 15-minute break? 5, 15, 10. All right, we'll just go 15. Okay. It looks like most people want, let's see how many votes. 1 for 5, 2 for 15, 1 for 10. We'll go with 15 then. That has the most votes. Okay, so 15-minute break we'll do. And then we'll start up again in 15. Okay. All right. Let me pause the recording here. So again, send me a message if you're trying to add, and then I'll give you an add code since it looks like I have plenty of room now. Now, what we're going to do is I'm going to stop talking about nomenclature. We're going to continue nomenclature next week on Monday. Let's have another quiz kind of thing. The final, not the final, the exam, we're having the exam on Tuesday. So this first exam is going to be a take-home exam. So I'll give you plenty of time to complete it. And so take home, and then you could do it at your leisure, and then you'll upload it. And so I'll have an upload link. I'm not sure how many. Well, you'll have plenty of time to be, I think, to be able to do it. And so let's do another quiz here. This quiz is going to be, let me make sure I'm sharing that. Yeah. Let's look at number 89 here. This is another challenging problem. And so we'll do this one as a group quiz. The exam, though, is not going to be a group quiz, let's say. Okay, we'll just break up the room into 4 to 5 participants. Eventually, if you give me a list of who you want to be paired up with or grouped together with, I'll set the groups that way, but this will just be random, whatever Zoom decides to create. And then can you work on this problem? Can you take a picture of this problem or just have it up? And let's create the room here. And so if you could just join a room and then work on this. We'll spend the remaining 25 minutes. Try to see if you can get this particular problem done in 25 minutes, if it's possible. And so there's a little bit of time pressure here. The time pressure you aren't going to necessarily feel on the first exam. The first exam is going to be really minimal time pressure, but on this I'm adding an element of time pressure, 25 minutes, try to finish it. But you could take more time if you want, it's fine. But a hard problem like this, you probably want to be able to do it in like 25 minutes or less, 10 minutes. 10 minutes would be great, But 10 minutes requires a lot of practice in doing these kind of things. So why don't you go ahead and join a group? If there's nobody in your group, then well, we can rearrange things or shoot me a little note. We'll try it. This is not everybody's present, I think. So give it a try and see, how this one goes. Okay, I see some groups only have two. Is that enough, or do you want me to redo the groups? Two participants. If you have any requests to move, let me know. I can move you to a different group. If there are any requests to move to a different group, let me know. Okay, let's see here. We're pretty much running out of time here. So what we're gonna do, I just sent out the little note. We're just gonna continue this quiz on Monday. And so if you're trying, again, if you're trying to add the class, send me an email or message on Piazza. I'll send you out an ad code. But anyway, have a nice weekend, you guys, and then I'll see you guys on Monday. You can hear me.